All right, welcome back to our three-part series on the natural recursive form. We are finishing up with this example where we have a uh, rational sequence, and the explicit part of it is fairly simple. If you look at the denominators here, you've got a 3, 4, 5, and 6, and the numerator could be easily found as well. 3n minus 1 is pretty easy to spot as we work through the 2, 5, etc. Now, writing this recursively is very tricky, especially if you're going to try to do this without using an n and just using a sub n minus 1. But I wanted to show you as a reminder of what we're doing. We've got just let's say that we had an a sub n which was just 2n. Then a sub 1 would equal 2, a sub 2 would equal 4, and a sub 3 would equal 6. And what we're trying to do is we're trying to write this term in terms of the previous term without using that n value right there. So what we actually have to do is we have to go backwards one step. That's the a sub n minus 1. Then we have to go back to here, which is an inverse. This is what we saw last time. And then we have to go forward by actually doing an a sub n. So we're going to do this little cyclical pattern here. And instead of doing it with a 2n, we're going to do it with our function that's been given here. Let's take a look at what that works out to be. Now keep in mind that that's what we did earlier. We just did it kind of manually. So the first thing I'm going to do in step 1 is I'm going to find a sub n minus 1. And that's going to be 3 times n minus 1 all over n minus 1 plus 2, or 3n minus 4 over n plus 1. The second thing I'm going to do now is find the inverse of this little function that I've created. So it's going to look like this: a sub n minus 1 inverse. Now we have a quick way of doing that. Let me just go back to functions. If you have f of x is equal to ax plus b over cx plus d, then you can find f inverse by just switching and negating. So it's going to look like this: dx minus b over negative cx plus a. That's called a switch negate. It reminds me a little bit of 2 by 2 determinants with, 2 by 2 inverses for matrices without the determinant involved there. So switch negate. So we're going to do that with our example here. We're going to end up with just an n, because that 1 comes up, and we're going to negate the 4, so plus 4. And we're going to negate the n, so negative n, and bring the 3 down. So it's going to look like this. So I've just found the inverse of that a sub n minus 1. And the third thing I'm going to do is I'm going to take that and I'm going to plug it in. Now keep in mind one last thing, that these little n's that I've got are actually going to turn into a sub n minus 1's in the end, because they're simple terms now. I'm going to leave them as n's. I'll replace those later. So let's go ahead and put this in. It's going to look something really strange like this: a sub n minus 1 inverse. And it's going to look like this as we plug this in. So it's a 3. 3, and instead of an n, we're going to have an n plus 4 over negative n plus 3 minus 1. And our denominator is going to be n plus 4 over negative n plus 3 plus 2. If we can simplify this out, we will have our recursive. So let's see if we can work this out. We'll multiply the top and bottom by the negative n plus 3, negative n plus 3. And I'll kind of zip this ahead a little bit. This is going to be 3n plus 12 plus n minus 3. And your denominator will be n plus 4 minus 2n plus 6. And I come up with a grand total of 4n plus 9 over negative n plus 10. And that is essentially what my recursive definition is going to be, except that I'm going to replace my n's with a sub n minus 1's. So here's the way it would look, our final solution. Of course, we always list the first term, so a sub 1 would equal 2/3, and a sub n is equal to 4 a sub n minus 1 plus 9 over negative a sub n minus 1 plus 10. And just for giggles here, let's go ahead and do the first term to see and verify out that it comes out to be 5 over 4. So we'll go ahead and just put that in there quickly here. So if I wanted to find a sub 2, that would be 4 times 2/3 plus 9 over negative 2/3 plus 10. Multiplying the top and bottom by 3 gives me 8 plus 27 over negative 2 plus 30. And finishing that out, that's going to give me 35 over 28, which is, let's see, dividing by 7 there, 5/4. So it does verify that the second term is 5/4, and you could go ahead and work your way down the rest of those if you wanted to verify it for yourself. But here we do now have a recursive definition for this nice little uh, original sequence that you see here, 3n minus 1 over n plus 2 in explicit form. Well, I'm going to finish out this video with one last example, and that is going all the way back to the beginning where we worked with the quadratic. So this time, I'm not going to write it out the way I did before. I'm simply going to do it as I just did a moment ago with that triangle technique. So let me write out a sub n again. So a sub 1 we know is going to be 2, a sub 2 is going to be 3, a sub 3 is going to be 6, and a sub 4 is going to be 11, and etc. down there. So keep in mind we're trying to do the a sub n minus 1 first. So number one, step one, we're going to figure out what a sub n minus 1 is, and that's going to be n minus 1 squared minus 2 times n minus 1 plus 3. So again, we're trying to realign our sequence so that the n minus 1 term, this one here, matches up with the next term rather than the one that it's at. So that's what we're doing there. It's going to be n squared minus 2n plus 1 minus 2n plus 2, and then plus 3. Or I guess I get an n squared minus 4n and plus 6 there. Okay, that looks great. Now we'd like to, number 2, find the inverse. So that's going to be a sub n minus 1 inverse, which is going to be a little bit tricky. It's a lot easier, of course, if we just write this as a y equals and all that. But let's go ahead and do it with the a sub n minus 1 just the way it is. So if it's all right, I'm going to erase. I'm going to go one step back here. I'm just going to take this problem that we have. In this particular case, I'm going to solve for n. So it's going to look like this. A sub n minus 1 minus 2 is n squared minus 4n plus 4. I subtract 2 from both sides so that I can complete the square here. So n minus 2 squared is equal to a sub n minus 1 minus 2. Take the square root of both sides. N minus 2 is equal to the square root of a sub n minus 1 minus 2. And so therefore, the n value, which we're going to substitute in just a minute, is going to be 2 plus the square root of a sub n minus 1 minus 2. All right, so we've gotten through 2 of the 3 steps. Let's go to the last step, which is to take this idea here. This guy is our inverse of the n minus 1 sequence, and so we'll go ahead and plug that in for n. So it's going to be a sub n minus 1 inverse is what we're plugging in. And that is going to be a little bit, I'm going to maybe need a little bit more room than this, but 2 plus square root a sub n minus 1 minus 2 all squared minus 2 times that 2 plus the square root of a sub n minus 1 minus 2, and then I'm left with that plus 3 at the end. So let's see if we can write this out. I'll put equals right here. We're going to get 4 plus 4 square root a sub n minus 1 minus 2 plus, now we take the square root off of this one when we square it, so it's going to be a sub n minus 1, excuse me, let me back that up just a bit here, minus 2, and then it's going to be minus 4, minus 2 of those, a sub n minus 1 minus 2 plus 3, making a little mess over here, but we can start collecting some terms. So let's bring that first term out front, n minus a sub n minus 1. We've got plus 2 of the radical a sub n minus 1 minus 2's. And I think the last term, if you add up all these constants here, I've got a 3, negative 4, negative 2. And then this one, I think we just get a plus 1 at the end there. Yep, plus 1. All right, double checking my work there. So that is supposed to be our natural recursive form. And let's test it out. This is going to be a sub n now. So we would then say a sub 1 is equal to, all the way back to the beginning, is the number 2. And then a sub n, or the next term, should be a sub 1. So let's take a look at number 2. So I'm using my recursive form. Now I'm going to use this form to try to find the next term. That's going to be 2 plus 2 times the square root of 2 minus 2 plus 1. Or in this case 2. This all comes to 0 plus 1 is 3. So it checks out as the first one. Now let's just go one more step to make sure that we can verify that for a sub 3. So we'll work it down for a sub 3. which should be the previous term a sub 2, which is a 3, plus 2 square root of 3 minus 2. And then that's going to end up as a 1. So 3 plus 2 plus 1, which is 6. And so you see that we do have ourselves a nice recursive sequence using just the a sub n minus 1. So here it is. You've got your a sub 1 is 2, and your a sub, oops, I'm making a mess again. There you go, right there. A sub n is that whole thing, and a sub 1 is equal to 2. So once again, this kind of shows a nice clean method for finding a natural recursive definition for this explicit uh, sequence, which is a quadratic, or in the previous case, a rational one. Hope you enjoyed that and give it a try.